I'm going to add James Turner in next, which is really exciting. Hi, James. Welcome.
Cheers.
And James is joining from the exact opposite side of the world, Australia versus Alaska. I mean, temperatures, differences, everything couldn't be farther apart.
Pretty much.
All right, so James is going to be talking about maximizing algorithm performance in a Levenshtein distance, which sounds really exciting. And I'm just going to turn it over and let you get going.
Yep. So yeah, this presentation is all about maximizing performance on an algorithm in .NET, specifically Levenshtein distance. Our goal today is to make an extremely fast Levenshtein distance calculator capable of handling very large strings. Created by Vladimir Levenshtein, the Levenshtein distance algorithm answers the question, how similar are two strings? The smaller the distance, the fewer the differences there are. The algorithm does this by iterating over the characters in two strings, identifying the edit cost depending on the operation performed. There are a few different applications for Levenshtein distance. Working with smaller strings, you can identify how similar two words are, useful for spell checking suggestions. For larger strings, you might be comparing two files, useful for things like plagiarism detection. Calculating the Levenshtein distance for two strings is a relatively straightforward process. In this example, we will calculate the distance between Saturday and Sunday. Imagine a matrix of the letters of these words, making the columns and rows. The algorithm operates on a cell-by-cell basis. The cell with the hash symbol is the first cell that we calculate. The left cell represents the insertion costs. The cell above represents the deletion costs. And the top left cell represents the substitution costs. We use these different cells together to find the value for our current cell. We start by taking the minimum value of the insertion and deletion costs for our cell, adding 1 to the result. This gives us the value 2. We then take the substitution cost for this cell, adding 1 if the corresponding characters in the row and column don't match. The letters in this row and column are both the capital letter S, so we don't add 1, leaving us with a value 0. Finally, for this cell, we take the minimum value of the two other numbers we just calculated. This means that the value for our current cell is 0. We repeat this process for the next cell in the row. We have an insertion cost of 0, a deletion cost of 2, and a substitution cost of 1. Following the same formula on the previous slides, this gives us the result of 1. Repeat this process for every cell in the row, and repeat that for every row in the table. The Levenshtein distance is found in the last cell in the bottom right corner. This means that the Levenshtein distance for Saturday and Sunday is 3. This is our baseline implementation in C#, where we will iteratively build upon throughout this presentation. There are 3 essential elements to our baseline: the data structure, the data initialization, and the main calculation logic. Starting with the data structure, we are creating a jagged array of integers via link. This structure mimics the same way we visualized the calculation in earlier slides, a full matrix of rows and columns. Next is the data initialization. We need to set up the first row and the first column so we can calculate the data. The first loop handles the first column, while the second loop handles the first row. Finally, we have the main calculation logic. Going row by row, column by column, we are grabbing the individual insertion, deletion, and substitution costs, finding the minimum value and storing it in our matrix. Benchmarked using .NET 5, our solution doesn't seem to perform too badly. In a little under 400 nanoseconds, we've calculated the distance between our two strings. These were two small strings though. How does it work if the strings were a few thousand characters long? As implied by the big O notation on the previous slides, the algorithm doesn't scale well at all. To achieve our performance goal, we will need to use a combination of .NET features and get a better understanding of the algorithm itself. Let's start with the algorithm. At any single point in time in the calculation, we only care about the current and previous rows. So why do we create a whole matrix for the values? Instead, we could alternate between the two rows of data. This would dramatically decrease the memory requirements for the calculation. While this improvement should not be understated, we can do even better than this. If we had one row, it can represent the deletion costs. The substitution and insertion costs start from a known point, 0 and 1, so we can use two variables to track that. Once we calculate a cell, it is a matter of shuffling our insertion, substitution, and deletion costs around. Here's an example of what that might look like in C#. While the link usage would have contributed to our allocations, the biggest win here is the lack of the jagged array itself. We also gain a small benefit from removing one of our data initialization loops. So what effect does this have on our allocations? Our single row variant is significantly faster than our baseline. We've removed over 99.9% of the allocations in our 10,000 character example, and this calculation performed far faster. All these gains are from just taking a closer look at the algorithm and how we can be smarter with it. For the little memory we are still allocating, we can now use a feature in .NET to remove it entirely, called array pool. Every call to get distance was creating a new array for tracking our row of edit costs. Instead, we can rent an array from array pool, avoiding the allocation costs associated with creating a new array. We do our calculation as normal, but before we finish, we take our result out of the array and return the rented array. Returning the array is an important step. It isn't free memory. We need to return it so other code can use that buffer. When used properly, the array pool can be extremely useful. From such a small change to our code, our memory allocations are now gone. We've even had a small increase in performance. Array pools work great in our scenario, though there are a few things to keep in mind if you're wanting to use it yourself. There is a great post by Adam Sitnick about array pool, which goes into depth about some of the quirks. Now that our memory issues are effectively solved, let's continue improving performance by taking another look at the algorithm. There are a lot of cells to iterate in our matrix. It'd be great if we could reduce it. It turns out strings with a common start and end can be trimmed with no change to the result of the calculation. In the matrix on screen, I've highlighted the area where the differences between strings as well as the outer boundary, representing the insertion and deletion costs. What we see here is effectively a mini Levenshtein distance matrix in what we were already working on. Factoring this in, we can shrink the area we need to process by a significant margin. While not all strings share a common start and end, when they do, it can dramatically increase our performance. Implementing this logic in C# isn't terribly difficult, but it can be a gotcha depending how you go about implementing it. On the screen now is a fairly basic way in C# to achieve our desired trimming for both the start and end of strings. This code, however, isn't optimal. Near the bottom of the snippet, we're creating a substring. This is a new source of allocations. The larger the substring we are making, the more memory we are allocating, working against our earlier efforts to improve memory usage. Instead, with just a few tweaks, we can avoid allocations by using another feature in .NET. By switching from substring to using span slice, we can avoid creating a new string on the heap. This works because a span is a span of memory, pointers, arrays, or in our case, strings. A span lives on the stack and just points to specific segments of memory. So when we slice it, all we are doing is creating a new span with a new offset and length. The behavior of span works well in our use case. We don't need a new string specifically. We just want a slice of the string to work with. We keep all of the main trimming code shown earlier, with our changes only starting from the slicing instead of using substring. Because we are using a new variable, we need to change a few references to the rest of our code. That said, it is otherwise a drop-in replacement, as span supports indexes and has a length property. The performance of trimming will drastically depend on the input strings. In this specific benchmark, there are two variations of 100-character strings, where they do or don't share a common start and end. When they don't share one, performance is slightly worse for our trimming variant. This is to be expected. We are doing extra processing work that turns out to have no benefit. When they do share one, it can help the calculation perform far faster. You might have noticed that our previous variant without trimming support also performs a little faster when strings have a common start and end. This relates to branch predictability. The performance of Levenshtein distance can vary drastically by how predictable the data is. This is because our code has a lot of branches, and the larger the string, the more branches that are processed. we can enable some hardware counters to see how many branch instructions and branch mispredictions we have to understand the impact of our branches. While there are limitations to the accuracy of the hardware counters available, we can still get a general idea of how the performance characteristics change. What we can see though is that our slowest test case, the one with random data, has the most branch mispredictions. As a reminder of our branching situation, this is our inner loop of the calculation logic. We have 3 branches, one for checking the characters between the 2 strings and 2 for doing the minimum value logic. These branches are run on every iteration of the loop. The problem with our branches is how often our inner loop is called and the potential randomness of our data. The longer the strings we are comparing, the worse our inner loop performs due to those branches. We can reduce the number of branches we process because the Levenshtein distance algorithm has another trick up its sleeve. The algorithm requires the lowest of the insertion, deletion, substitution values. On screen, I've highlighted all of the cells where the 2 characters match. Remember, the rules for calculating distance, we only add 1 to the substitution cost if the characters are different. Insertion and deletion costs, on the other hand, they always have 1 added to them. In all cases where the characters are the same, their substitution cost is the lowest value. Knowing that, why do we do 2 math min calls when the characters are equal? Instead, we can use the substitution cost directly. Replacing our ternary operator with a full if statement for our character comparisons, we can wrap our math min calls. This makes our best case, where the characters are equal, have 2 fewer branches. Our worst case, where the characters are not equal, have the same number of branches. Performance-wise, we are seeing a measurable speed up across the board. The hardware counters, while remembering their accuracy limitations, show a large difference on our predictably equal test case. Strangely though, there is a speed up on the predictably not equal path, though there should be no less branches on that path. The thing about optimizing on this level is that we can have a cascading changes with how the JIT processes our code. We can see this to some extent with the additional code size column in the benchmark results. Code size is the total size of the CPU instructions to execute our code. Our updated version has 42 less bytes of instructions, and all we did was reorganize our code. To understand the impact of the JIT optimizations, we need to see what the JIT is generating. There are a few ways we can view the JIT's generated assembly, like SharpLab or Benchmark.net's disassembly diagnoser. With access to the assembly code, we can start to see how small impacts to our C# code affect the JIT. Here is a short example, unrelated to Levenshtein distance, to show you how small changes can affect our generated assembly. On the left, we are accessing 2 array items and multiplying the results. You might think then the right would just access the values and, well, multiply the results. Instead, we have 2 branches indicated by the jump instruction labeled JBE. You can see both jump instructions go to the line L0017, a call instruction. The branches and that call are all to do one thing, bounds checking. What if we changed our C# code slightly? What if we swapped the 4 and 5 around? When swapped, we have a smaller assembly output with 1 less bounds check. It can do this because knowing that it can access index 5 correctly, it can access index 4 correctly without needing to check. This is what I mean by small changes to our code having a larger impact on the JIT output. This output is arguably faster for having 1 less branch, as well as less instructions overall. Now we've seen the impact of small changes to our C# code on the JIT, let's have a look at our example with the calculation logic where the JIT could do with some help. During the calculation, we are comparing a character from the source and target strings together. The source character is determined by the outer loop, whereas the target character is determined by the inner loop. Our C# code, though, accesses the source character in the inner loop. The JIT, however, doesn't notice this, leaving our data access in an inefficient position. With only so much time to optimize code and only so many patterns it can recognize, cases like this might simply not be optimized. We need to be mindful of how we write code, as the JIT can only do so much. So in cases like this, we should give the JIT a hand. From a business logic perspective, we are doing the exact same operation. However, now we are being mindful of our usage. In our current suite of benchmarks, we can pick up a small change in both performance and code size. The performance difference is small, however, will scale with larger target strings. The change is also allowed to tweak the JIT to tweak other related parts of the assembly, allowing a slight reduction in code size. For a bigger increase in performance, let's look at something a little more unsafe. Pointers. Let's change our use of spans as well as our rented array to be accessed via pointers instead. Pointers automatically make things faster, right? The short answer is yes, pointers did automatically make our code faster and even decreased our code size. The downside is that our code is now unsafe. Our performance improvement is primarily coming from the fact or from the lack of bounds checking that now occurs. If we write to the wrong memory location, we can easily corrupt the program. I had this happen numerous times during my research for Levenshtein distance, so that was a whole lot of fun. With that in mind, it is a good idea to have extensive testing around the use of pointers just to make sure you don't corrupt your own application. Going beyond pointers, let's look at using hardware intrinsics to boost our performance. Hardware intrinsics is about accessing specialized instructions on a CPU that can accelerate our workloads. These instructions come from additional capabilities of specific CPUs that extend a base architecture. Since .NET Core 3.0, we can access these additional instructions to accelerate performance in our applications. The majority of these instructions relate to a concept called single instruction multiple data, or SIMD. SIMD is a way that we can perform an action to a set of data at once, rather than individually. Work is performed on a vector, so in this example, we have two 8-value vectors, and we can add them together in a single operation. In Levenshtein distance, there are a couple of different ways we can use it, though there are some caveats. The core problem comes down to the fact that for us to do vector processing, we would ideally need a full vector of values. For Levenshtein distance, this is difficult to do in the main calculation, as we don't know all the values we need for a vector at the same time. Let's walk through the calculation if we try to vectorize it in the same way we've been processing it currently. Highlighted is the substitution cost for the first 4 cells. Loading that into a vector isn't a problem. We know all those values ahead of time. Similarly, with the deletion costs, we can load those into a vector no problem. How about insertion costs? Insertion costs become our problem, as while we know the first insertion cost, we don't know the next 3 to fully load our vector. Let's pretend we have the next 3 insertion values. So now we have all 3 vectors and we can begin calculating, but wait a minute, we have 3 of the 4 values we're going to calculate anyway. What this means is the 4th value of the resulting vector would be a value we didn't know ahead of time. That's not useful at all. All hope isn't lost though. We can still make use of vectorization. Our trimming logic can take advantage of vectorization, as we can compare multiple characters at a time. The snippet here is a small part of a larger solution, however gives the gist of our changes. Using AVX2, a capability for modern x86 CPUs, we can load our string into 2 256-bit vectors, allowing us to compare 16 characters at once. We continue with more AVX2 instructions, comparing values and getting a single match value. If any characters are not equal, we use some bit operations to find the final number of characters we can trim. I'm simplifying this for brevity, however, it is worth noting a number of specific additional considerations. Not all CPUs support all instructions. What the snippet doesn't show is a defensive check to confirm AVX2 support, falling back without it. Ideally, falling back to use 128-bit vectors with an older instruction set. These are some of the things to keep in mind if you're using hardware intrinsics. This is a specialized benchmark for string trimming where all characters are trimmed. While we have a small performance regression at 10 characters, we have hugely increased our performance in any strings that are longer. Just look how much faster our 1,000 or 10,000 character trimming has performed. Depending on your workload, with the right use of SIMD and other hardware intrinsics, you can have huge performance gains. It is worth noting, however, that our code size has increased quite a bit. Now for something a little more unconventional, using SIMD in a way it likely isn't intended. I said earlier that the main calculation, with the way that we process it row by row, can't benefit from SIMD because we can't load the full vector. While that is true, it's somewhat of a half-truth. There are ways that we can still benefit if we try hard enough. On screen is the before and after of swapping out the core calculation logic for Levenshtein distance. There is a lot of vectors being used, but if you look carefully, the vectors are all loaded with the same value in all positions. It is equally as wasteful computationally, however, follows our previous logic closely and ends up removing the minimum value branches for us. With less branches for the CPU to worry about, our code ends up improving in performance. From 10-character strings to 10,000-character strings, it beats our previous best and crushes our baseline. Still though, what if we need to work on bigger strings? This is where we take everything we've learned about Levenshtein distance so far and make it multi-threaded. To help demonstrate how we can do multi-threading, I've split the matrix into two regions to show you how two threads would work. At the start of calculating, we need to complete the first row for the first region in a single thread. Once that row is complete, that thread can continue on its next row. At the same time, the next region over can start on the first row. This process works this way because of the dependency of insertion and substitution costs across regions. The right thread needs the left thread to process the row first. Adjacent regions need to share a buffer between threads to access the insertion and substitution costs. The left thread writes to it, and the right thread reads from it. When implemented well, we can scale across CPUs with many cores, allowing processing of huge strings in a reasonable time. This multi-thread variant is configured for a minimum of 10,000 characters per thread, avoiding the overhead on smaller strings. It still takes advantage of everything we've talked about so far: a single row for data structure, using array pool to reduce allocations, with our branch improvements, using pointers, and our other vectorization tricks. On my test machine with 4 cores and 8 threads, the 100,000 character benchmark uses 8 threads, which led it to an 83% performance improvement. On a machine with more cores, it would likely be possible to scale this further for handling even larger strings. Beyond everything I've talked about so far, there are still other ways we can improve performance. We can fine-tune our assembly output, look up what instructions perform the fastest, and massage our C# the right way so the JIT generates what we want. Our data initialization. We could write a vector of data to a pointer, filling the row 8 values at a time. Loop unrolling is also effective. While there are certain things to be aware about when doing so, it further reduces branches, increasing performance. Or a really interesting technique of processing our data diagonally, allowing us to really use vectors to their full advantage. I can't fit all of this into a single talk, so let's finish up on some key points to improve performance in your own code. Have a performance goal. This is really important. You need to know why you're optimizing. Our goal from the outset was for handling very large strings. Now we can tackle strings over 100,000 characters long. If we were writing this for a spell checking application, the later optimizations are mostly not needed. When you know your goal though, it's important to keep measuring your changes on your path to get there. The various benchmarks throughout this talk showed measurable performance and allocation changes, so we knew that we're making progress. Our initial progress came from gaining a better understanding of the algorithm. While I might have been talking about Levenshtein distance, think about the code that you were working on. Reframing the problem you are tackling with an algorithm might give you more insights to dramatically improve performance before doing anything exotic. Finally though, knowing the tools that you have available can help unlock additional performance. We removed allocations with array pool, avoided other allocations with span, and gave even more performance with hardware intrinsics. No doubt there are new tools and features coming to the .NET runtime that will continue to help us improve performance in our applications too. Finishing up, you can find my highly optimized version of Levenshtein distance, called Quickenstein, on GitHub. It has every optimization I mentioned today, including the ones I couldn't cover in detail. It is quite possibly the fastest .NET implementation for calculating Levenshtein distance. Additionally, all benchmarks and code from this talk are available on GitHub. Thanks for joining me on my talk.
Oh, sorry, I forgot to add myself. I switched to the 2-person view and it doesn't add me. Thanks, that was awesome, James. That was really exciting. So when I first started programming a long time ago, I was learning how to do like a search algorithm, and of course, Levenshtein comes up, and I helped implement it in a SQL Server stored procedure. I'm pretty sure it wasn't fast. Definitely wasn't as optimized as yours, but whew, yeah. Fun stuff. All right. So there are a couple questions, and actually I want to switch to my screen, not yours. There we go. Yeah, it was interesting. So we got a question that came in. How would I go about writing an algorithm to determine whether someone prefers fresh or smoked salmon? I was considering a Markov chain, but maybe some kind of neural network would be better. What's your thoughts, James?
Well, I would say that I have no idea. My experience with algorithms, at least for the last little while, it's been so laser focused on Levenshtein distance that I couldn't probably explain the difference between a merge sort and a quick sort.
Understandable. I mean, there's really only one option is you've got to get the fresh salmon that you grill and smoke so that way it's smoked and fresh and you get the best of both. I mean, it's really the only way to cook salmon is to smoke it on a grill. So that's just my 2 cents. What do I know though, right? um, what provoked you to start really digging into this? Did you just love pain? I mean, what was your thought process here?
So I was building an application where I needed to compare web pages and I wanted to see how much was different between web pages. A web page I was actually trying had 200 and something thousand characters, and I tried to run it on that baseline version, and that took like 30 something plus seconds to calculate and was taking gigabytes of RAM. I'm like, yeah, that's not going to work if I'm going to use this as a service. So let's try and optimize it. So some of the initial optimizations were relatively simple. I was looking at how other people did it in other languages and just being like, well, does that translate well to .NET? And most of the cases it did. Some of the like JIT optimizations, that was kind of just random stuff I discovered along the way of, hey, wait a second, if I do this and that, then it can work together. The one that I didn't really get to touch too much in the talk, I only mentioned it briefly at the end, the diagonal processing. I can't remember the person's name, but they implemented it in C, and it's so much faster. So like I've got that in my Quickenstein version, but it's amazing that like when you just change how you process the same algorithm, you can get dramatic performance improvements.
Wow, that's really exciting. So basically, if you run it on news sites, how closely are they basically all the same, right?
Oh yeah, it depends. Like I wanted to see like if you modified an article, have you modified an article by a significant amount or a not significant amount? And Levenshtein distance can allow me to do that. But then you know some blog posts and stuff can go like tens of thousands, hundreds of thousands of characters. I mean, the one probably for the .NET 5 release is probably quite long.
Do you see many changes? I mean, I'm guessing typically it's basically the same thing.
Oh, I mean, it depends. Like, if you crawl a website at one point and then you crawl it again in another, you could see drastic differences, but they could just be from that someone's changed the UI. So you need to then differentiate between that's the part that I'm doing here or something else. But it could be good, say, even for like comparing revisions of books, because if you've been sold a new revision of a book, but it's got no significant difference, then you might be like, well, I'll just take the previous version.
That's awesome. Well, hopefully you continue your work and you can get the C# one as fast as possible. I have faith in you. You can do it.
Cheers.
Looks like you're on the right track. All right. Thanks, James, for coming and joining us. It was an awesome talk. I'll have to watch it again later. Thank you.